Viewers, welcome to chemistry class with the science demystifier. In today's video, I will be teaching you fragmentation patterns in esters, that's the alkaloids. Now remember that fragmentation is an important aspect of mass spectrometry. Why is it important? Because it enables you to predict the likely peaks that can be obtained in the mass spectrum using the M to Z ratio. Please don't forget to subscribe to my channel. Also, turn on the bell notification for updates when I'll be posting more videos like this. So, you can also share this video to your friends, people that you know that can benefit from this content. Undergraduate students and also chemistry students at the MSc level. So without wasting much of your time, let us go to the board and demystify the process. Alright, so here is a case study here. We have the compound propyl ethanoate. So we are going to show the different fragmentation patterns in this compound. But before I start, I would like us to look at different bond cleavages we have in fragmentation. One is called the homolytic bond cleavage. The homolytic bond cleavage. In homolytic bond cleavage, the electrons in the bond are equally shared between the participating atoms. In heterolytic bond cleavage, the electrons in the bond heterolytic. The electrons in the bond are shifted to a more electronegative atom. The electrons in the bond are shifted to a more electronegative atom, which results to the formation of a carbocation. Then we have the third type of fragmentation, which is known as the Claffertis rearrangement. The Claffertis rearrangement. So we are going to be using all these bond cleavages to explain fragmentations in propyl ethanoate. Right, so in the ion source of the mass spectrometer, a beam of electron hits the molecule from this angle. And when that happens, one of these electrons will be dislodged from the molecule, resulting to the formation of what? A positive ion. So the molecular ion that will be formed, the resultant molecular ion that will be formed, becomes unstable, which results to what? Fragmentations. Now let us see, first of all, the type of fragmentation that can occur in this molecule. And that is the cleavage of this bond here. The bond between carbon and oxygen here can be cleaved. And that can happen either homolytically or heterolytically. Then if it is a homolytic bond cleavage, remember I told you that bond cleavage can be homolytic or heterolytic. And I said that if it is homolytic bond cleavage, that the electrons are equally shared between the participating atoms. So assuming that that is what happened here, so one electron goes to this oxygen, resulting to the formation of what? A free radical. So this free radical will not be detected in the mass spectrum because it is not charged. Then the remaining electron will go to this point, to where we have the double bond. It will be attracted to where we have the double bond. Then one of these electrons here can also come down to that point. And when two electrons are gathering at a point, it results to the formation of a bond. So since we have two electrons going there, so that is what that will lead to the formation of a triple bond with a positive charge. So this particular ion will definitely be detected in the mass spectrum because of the positive charge on it. So the charge to mass ratio, the mass to charge ratio of this molecular ion is, of this fragment, can be obtained by adding all the masses of the atoms present. So here we have 24 grams because of 2 atoms of carbon added to 16. 24 added to 16 will give us 40. And then we'll now add 3 atoms of which is 43. So don't forget that the molecular ion itself has its own charge to mass ratio, which is the molecular ion, the mass of the molecular ion. And you know what the mass of the molecular ion can be used to achieve in mass spectrometry. It is used to determine the molecular mass of the compound itself. So the M to Z ratio of this compound is obtained by summing up all the masses of the atoms, how many carbon atoms, how many oxygen atoms, how many hydrogen atoms. We put them together to get the mass of the molecular ion. So the M to Z ratio of the molecular ion is what? 102. So that means there will be a peak in the mass spectrum at 102, which shows the mass of the molecular ion. Okay, so we have already obtained one fragment whose mass to charge ratio is 43. Now let us look at another possible type of cleavage that can happen in the same carbon-oxygen bond, which is this point. Alright, so this bond can also cleave heterolytically. When it cleaves heterolytically, what happens? It means that the dislodging of the electron took place at this point. So it's no longer here that the beam of electrons struck the molecule, assuming that this is a target point. So this point will now result to the transfer of electron from this point to this electronegative atom. So this electronegative atom is the one that is receiving the electron, which will now make this ion to become what? This carbon now become positively charged. This carbon, because all the electrons are shifted to the electronegative atom. So it makes this carbon to become a carbocation. So resulting to the formation of this fragment. So this is another fragment that can be obtained from this molecule. So we now have CH3, CH2, CH2, CH3 as a neutral molecule, which will not be dictated in the mass spectrum. Okay, let us proceed to another type of fragmentation that can occur in the compound. So another possible type of fragmentation that can take place here is when the electron is dislodged from this point of the molecule. So when that happens, there's every possibility that this bond can homolytically cleave. And when that happens, one electron will come to this point. Remember, here we have a pair of electrons, a single pair of electrons, which can also trigger one of these electrons to come down here, so form a triple bond. So at the end of the day, we'll be having CH3CO with a triple bond, and it's going to be a free radical. So at this point, we're going to have O with a positive charge connected to CH2, CH2, and then CH3. So this one is going to have mass to charge ratio of, we have 36, that's 3 carbon atoms, plus 16, which is 52, then plus 7 hydrogen atoms, and that is 59. So we're going to have a peak at 59. So for this fragment, which will be dictated in the mass spectrum. Another type of fragmentation that can occur in propyl ethanoate is what we call the alpha cleavage. The alpha cleavage is the breaking of the carbon-carbon bond. There's a bond between these 2 carbon atoms. Why is it called the alpha cleavage? Because the carbon that is bearing the carbonyl functional group is called the alpha carbon. So the next one adjacent to it is called the beta carbon. So when this bond cleaves, it is called the alpha cleavage. So the alpha cleavage is always a homolytic bond cleavage because the atoms participating in the bonding process have equal electronegativities. So the electrons here will be equally shared. One coming to this carbon here, and then one being attracted to this point where we have the double bond. Then this electron here will come down also to that point, will be attracted to that point, resulting to the formation of another bond. So the total bonds we're going to have there will be a triple bond. It will be a triple bond. Remember that there is a positive charge here, which came as a result of the dislodging of electrons, by the beam of electrons. So this molecule is already positively charged at that point. Then we have OCH2, CH2, and then CH3. So this is another type of fragment that will be obtained, while the methyl radical will be given off as what? As a residual free radical. So this one will not be detected in the mass spectrum. So to obtain the mass, the peak that will be shown on the mass spectrum, to obtain it, you simply need to, because metal is 15. Metal has a mass of 15, M to Z ratio of 15. So to obtain the mass of this compound, you simply do the mass of the molecular ion, which we obtained as 102 minus 15. So this will give us 7 here, and we have 8. We have 87. So the M to Z ratio of the molecular ion that will be detected in the mass spectrum will be 87. So there will be a peak at 87. There will be a peak at 87. Another type of fragmentation that may likely occur in this molecule is the fragmentation that will result into the formation of what? The propyl radical. Now, when the bond between this carbon and oxygen cleaves heterolytically, why? Because the oxygen atom here and the carbon atom here have different electronegativities. So that will result in the shifting of the electron from this point to this point, resulting to the formation of a carbocation at this point. So when this bond cleaves, I said propyl radical. So it's not a propyl radical because this is propyl with a positive charge. So it's going to be a propyl ion because it's having a positive charge. Okay, so this will result to assuming that there is the cleavage. The molecular ion was hit from this point. So the pair of electrons in this bond has shifted to neutralize this positive charge. So resulting to a neutral molecule. So we have COO, a neutral molecule. Then this particular one is now carrying a positive charge. Why? Because the electrons were all shifted to the oxygen atom, so resulting to the formation of a positive charge. So this is a possible fragmentation in this molecule. So let us calculate the M to Z ratio of this molecule. So we have already 3 carbon atoms, which is 36, and 36 plus 4 will give us 40. So we're going to have a peak at 43 because of the propyl ion that we have generated. So that is another possible type of fragmentation that can occur in this molecule. Another type of fragmentation that can occur in propyl ethanoate is the one we call the Clafferty's rearrangement. What is Clafferty's rearrangement? It's a type of rearrangement reaction whereby the gamma hydrogen is transferred to the carbonyl oxygen. That is, the gamma hydrogen here is transferred to the oxygen at this point. That is what we call the Clafferty's rearrangement reaction. And during that process, an alkene is formed as a residual product. So now let's look at the mechanism of the reaction. the carbon that is attached to the hydrogen, the bond that is linking this hydrogen to this carbon, is homolytically cleaved. And when that happens, an electron is transferred to this hydrogen, while one electron is transferred to this bond here. So this free hydrogen radical is now attracted to the oxygen side. Please don't forget that there is a single electron here with a positive charge, and then a single unpaired electrons at this point. So hydrogen is attracted to this part of the molecule. Then when that happens, at the same time, this bond, this alpha beta bond, will cleave as well. Remember, this is the alpha carbon and this is the beta carbon. So this alpha beta bond will cleave. So when that happens, one electron will jump into this place. So remember, this oxygen has a lone pair of electrons. So one of the electrons will also jump into that space to form a double bond. And then one electron from here is transported from here to join the other electron in the gamma beta bond. Remember, by nomenclature, this is the alpha carbon, this is the beta carbon, and this is the gamma carbon. Okay, so now the resultant ion or fragment we're going to get will look like this. It will look like this. So we have a double bond to oxygen having hydrogen attached to it now. Then we have a dot and a positive charge. Then we have oxygen, which is this, with a single unpaired electron. Here we have paired. So at this point, we're going to have another double bond connected to carbon, and that carbon is going to have two hydrogen atoms. So this is how the molecular ion will look like. Then remember that this bond has cleaved. So the whole of this molecule at this point will be an alkene, which is CH2 with a double bond and CH2. So that is to say that the double bond has been formed at this point at the gamma beta bond. Okay, so the particular ion that will be observed in the mass spectrum will be this one with a positive charge, and its M to Z ratio can be calculated by subtracting 28 from the mass of the molecular ion, which is the molar mass of the compound. So when we subtract 28 from 102, that will give us 74. So the mass to charge ratio of this ion is 74, meaning that we're going to have a peak in the mass spectrum at 74.